Test.
Terdengar, Ibu.
Good afternoon, dear all presenters and the other attendees, and welcome to the one of the morse 2021 parallel session. This is the parallel session for the Mechatronics paper category. I am Triana, will be serving you as the chair session of this parallel session. And based on our schedule, there will be 6 papers presented in this session. Each turn has a maximum duration of 20 minutes. The presentation should be conducted within 15 minutes. The presentation will be followed by extra 5 minutes for the Q&A session. I will be the timekeeper and notify the presenter if his presentation duration is about to finish. Therefore, let us proceed to the first presentation. The first presentation is for the paper titled Study Sensorless Sliding Mode Control for Permanent Magnet Synchronous Motor in Solar Tuk-Tuk. Is the presenter for the paper present?
Yes, madam.
Okay. Can you talk? Oh, yeah. I cannot hear your voice clearly. Can you volume up your microphone?
Now you hear me clearly?
Yeah, it's nice.
Okay.
Okay, Miss. Okay.
Now,
Dr. Piset. Okay.
yes. Now let me share my slide. Now we start my presentation. First of all, I would like to express my high respect to Madam Telina, the chair of the committee. And my name is Piset, and I'm from Cambodia. Currently, I'm a master student of Department Intelligent Mechatronics of Institute of Technology of Cambodia. This is my topic that I will present today. My topic is study of sensorless sliding mode control of permanent magnet synchronometer in solar Tuk-Tuk. This is my content. The first introduction and the current solar Tuk-Tuk system, and the third model of the permanent magnet system, and one more sensorless control method, and one more simulation study, simulation result, and conclusion. First introduction. Nowadays, the environmental in the environment is sorry. Introduction, I start from environment because nowadays our environment is not good, and our overuse of the fossil let's make our environment to not good now, and want to make environment more better by technology by replace the gasoline to use electrical vehicle that is the most popular in my city. The is very cheap and fast, but they use all gasoline, so I want to replace them by electric and by using the sensorless, by reduce some cost of the tuk-tuk, and by using the PMSM to make propulsion of tuk-tuk. So that's why I chose this topic to study on the sensorless control of permanent magnet synchronous motor. For the system of the tuk-tuk, we may see the two domains of the system. First is the energy storage system, then called ESS. It's like a battery or capacitor or PV panel that we use to store the energy or to make energy for the electric device in the tuk-tuk. And the second one is the electric propulsion system called EPS that have a motor or another mechanical propulsion that to make the tuk-tuk moving. And my objective is to make an optimal control of the permanent magnet synchronometer. And the second one is the sensorless control. Let's make it less complex and less hardware cost. For this is my my objective that I will define. And the scope of the objective and the scope of the whole of my project is I design the control system for 1 kilowatt of PMSM and investigate the observer to estimate the position and speed with effectiveness, robustness, and low cost. And develop the sliding mode control of sliding mode observer for the estimate the position and the speed over speed range. And the last is simulate with the MATLAB simulating for testing the control system. And for the mathematical model that I start from the equation of the SMO and the PMSM, that I start from this to find to make block for the MATLAB control or for the MATLAB simulating, and test it to find the with the real of the motor that we try to make with the sensor first, and we try to replace the sensor by using the equation that we create in the MATLAB. And the first thing that I have done is make the with the simulink for the hardware, because the COVID-19 we cannot enter the lab, so we cannot testing with the real hardware, so we can finish the simulation with the MATLAB from the equation. And for the sensorless control, we choose sliding mode observer, because the sliding mode observers that we design allow the equation model and SMO for the estimate of the speed and the position. And the method that we define the speed and position of the PMSM, it's there are many ways that we can find, but we choose this one for the better way to find the speed and position. And we start from the voltage input, and we create a block for the PMSM and the observer by using the sine function for filter of the system, and to estimate the rotor position and speed by equation that I showed in the previous equation, and we get the feedback to find the correctness of our estimation. And this is the function. This is the block that I designed for my my observer, and we and this is the system of my research, that I have one input for my system for omega stand for the speed of the rotor that input, and we transform it to the to ABC frame for our motor, that we convert to, that we use this three ABC frame to our current controller, that convert to like PWM to inverter, and then inverter before use with the PMSM, and we use the feedback for the motor that we define with the PID, and lastly we design the observer for replace the sensor of our system that we define as a more observer that I show in the previous slide, and use the feedback of the speed to feedback with our reference speed, and try to find the error of the speed then we input and output of the estimate. So this is my speed, my system, the whole system of my PMSM control system. And we also install it in our lab, but during COVID pandemic, we cannot enter the lab, so we cannot test with a real experiment. And but if we use this motor for my experiment for our Optical that we use with solar, and you see the result of my research for simulation result. Firstly, I use it for I test it with the very speed that start from 50 radian to 250 radian per second. So we can see that the red one is the estimate speed that we estimate from our observer, and the blue one is the actual speed that we get, and this is the green one is the reference speed that we input. So we can see that our estimate can working correctly with our input, so it's tracking perfectly. And the second one we try to use with the load, and when in this case we use the stable speed for the 250 radian per second for our motor, and at the 0.5 second we input the load for Newton met, and we can see that when we input
I think Dr. Tok got some technical problem. Dr. Tok. Okay, I think I will proceed if Dr. Tok. Yes, Dr. Tok. Yeah, Dr. Pisat is not in the room right now. And therefore, unfortunately, we should skip the Q&A and we proceed for the second paper presentation. Okay. For the second paper, the title is Self-Check in Access Control Kiosk with Automated Card Dispensing and Storage System. Oh, Dr. Tok Pisat. Dr. Tok. Oh, Dr. Tok. Okay. Okay. We just proceed with the next presentation. I have Dr. Leonard Trusley already here.
Hello.
Dr. Leonard, the stage is.
Thank you for the time.
I cannot hear your voice.
Can you hear my voice now?
Still no.
Hello?
Yeah.
Okay. Sorry about that. Thank you for the time and the opportunity to present in this conference, Brianna. My team member is here, Havret Lucius. So Havret will be presenting for our team here on self-check-in kiosk. Havret, you can go ahead and share screen and
All right.
our presentation. Thank you.
Right, everybody see my screen?
Yes.
Yes. All right.
Yes.
So without further ado, I would like to begin my presentation. So for today, esteemed guests, thank you for participating. I will present our project, Self-Check-In Access Control Kiosk with Automated Card Dispensing and Storage System. This project is led by Dr. Leonard Rusley, and run by me, Havret Lucius, of Swiss German University's Faculty of Engineering and Information Technology. So how did it all started? So the background is, we see a problem. We see a problem that office buildings in Indonesia still use traditional method of card exchanging, which is by using a receptionist or probably a security guard. You can see this common in government buildings, in office towers, in complex where you live. Yeah, and this is not only a time-consuming thing where sometimes security guards or receptionists have to go through hundreds of cards just to find your card. So it's time-consuming and it has a human factor which causes lower security. And of course, it's not unlike a robot, it doesn't work 24/7. And of course, humans have limited memory. So yeah, by implementing automation, we plan to change this system, which is yeah, we hope to implement automation to the system. I know what you're thinking, but automation does not steal human jobs, but replace humans' menial task. I'm sorry. Okay. Base problem. So when we started this project, we have the most underlying problems are the uniqueness of this project lies on retrieving and storing mechanism, because most card storage systems are dispensing only. Inventory system back and forth. So like ATM machines MRT tickets, it's a one-time thing. You put in your card, you get out your card. So it's not storing or dispensing. And but this system requires an inventory system. You need to store and then you return your card. So back and forth. Of course, the key factor is identification. We need to identify whose card belongs to who, so that we don't replace, let's say, Ms. Triana's card to Mr. Leonard's card, right? Most system does not require to identify data. For example, your ATM cards are not identifiable. It's only the chip that's being read. And of course, fully automation. Conventional building access security is volatile. That's what I meant by human intervention. Because human intervention, you have feelings and emotions involved. So with this system, by implementing this automated system, data is stored in the cloud and can be tracked, right? So the objectives of this project is to construct a reliable mechanical design for storing and dispensing mechanism, a prototype of card storing and dispensing mechanism, identification of cards with optical character recognition, and record and log information of guests that access the machine, timestamp, and assign access cards. Right. So continuing forward, this is the overall mechanical design of the 3D design of the system. We have a double decker. So on top is everything that has to do with the user, the guests. So you have the card storage, you have the solenoid housing, you have the card scanning station, and that we have all the electrical components required for the system. And yes, so this for the explanation, I'll dissect into two: the card scanning station and the card storage carousel. So as you can see, the card is stored from A, and then it's scanned at A, and then it's the card is stored in B in the carousel. Moving forward, we have the card scanning station design. This consists of 6 modular 3D printed cards, and the main purpose, the main job of this card scanning station is to feed the card into the system. But before it enters, it has to scan the cards prior to storage, so that we have the data we need to read the card. So we have a chamfer, so that when inside, I'll explain further. Continuing forward. So this is what it looks like in real life. It's 3D printed, and it's 6. Why is it 6 modular pieces? It's because it allows it allows access to easy installation. Okay, so you don't have to have one piece that's fixed, and you can't do really much about it. Yeah, so it's easier to manufacture and easier to install. Okay, for the card storage carousel, our card storage carousel can store. On this design, on this project, we built a 50 card storage. So maybe further development of this project can increase the amount of slots the cards can be stored. So we have a lazy Susan as a base support, and then a 2mm acrylic and 1mm metal sheet as the base to just align the cards, and center extrusion support for a 3mm acrylic, so that the card just don't tilt more than 3 degrees for the solenoid to push. Why not just build an entire acrylic piece, right? If you ask, so it's because of weight, yeah, to reduce weight and for access of installation. So this is the top view of the card storage carousel design. We have a slot mechanism, so to ensure that the top and the bottom acrylic pieces are perfectly aligned. And on top of the bottom acrylic, we have a metal sheet for the support of the cards. Why metal? Because it's slippery. It's nice for the card. It doesn't corrode. It doesn't break easily. It's durable. It's durable and slippery. All right. For the card storage mechanism assembly, as you can see on the left, the blue painted piece is the metal sheet, and then on the right you can see a home positioning sensor, a limit switch, just to make sure that the card is always the carousel is always at position 0. And we have 6 fasteners throughout the card storage mechanisms to ensure the top and bottom are always perfectly aligned. All right. For the full assembly, you can see this. So we have the solenoid housing on the left, and the card alignment mechanism is just enough so that the card just are kissed by the card alignment mechanism. And then we have the camera and camera stand on the perpendicular to the card scanning system, right? Take a look, because continuing on, it's all technicals and no more beauty of this mechanicals, guys, right? Okay, continuing forward, the electrical components for this project, we use Raspberry Pi, 1-stepper motor, 1 DC motor for the scanning, to just feed the card inside. The stepper motor is to ensure perfect positioning for the carousel system. And we have 3 micro limit switches to ensure the position 0, and then the card in the card scanning station. And then we have a solenoid to push the cards forward and backwards, forwards, 1 USB camera, and 1 power supply. All right, so this is the wiring result, as you can see, for the first base. Okay, it's pretty neat, I might add, yeah. And this is the electrical grid for the overall project. All right, and the programs that I implement in the system is SQL, for MariaDB, and PHP MyAnime for the database. Python as my main programming language, OpenCV and Tesseract for the optical character recognition engine, right? So the sequence is like this. We have three main systems. We have the homing procedure, just to ensure that the carousel is always at point 0. We have the cart insertion sequence, right? And then we have the cart exit sequence. Okay. Why do I separate this sequence into 3? Why do we separate this sequence into 3? It's because we implement this object-oriented programming, which is the class can be defined as a template that describes the functions the objects of its type support. So after one class ends, calling out the next class, calling out the next class, calling out the next class, and in result, it's all it becomes a function. Yeah, beginning with defining the class name and ends with calling out the next variable. Okay. For the database, we have 3. We have cards in slot. Now the purpose of cards in slot is to have the index number, the name of the cards. So in this case, we focus on Swiss German University's student ID, and then the slot number, and then we have the photo logging for the image, and then access card name. So for example, Ms. Triano, our remaining guest, will insert your KTP or your student ID, and then you get access card, let's say A4, right? And then the access card link will be to that card itself. And for on the bottom, we have data lists, which will track every members or guests that enter the building. So once you borrow an access card, it's time logged, it's time stamped, so it's really accurate. You can't lie through the system. So, and then we have the slot, which just provides the data to the stepper motor of how many steps it has to move. Okay, I will now show you a video of just to get a real image of the demonstration. Okay. So in this system, we have the homing mechanism, homing procedure. So we have to align everything to base 0.0. Okay. Now this is the big thing, guys. Card insert will be driven by the feeding system into the card scan station. As you can see, it's driven in. Now the card scan station captures an image and is processed by the OCR engine, right? The card ID information will be uploaded to the database and linked to the assigned access card, which is A1 for this instance, because A1 is not borrowed yet. So, and the storage will rotate to the index position, delivering the assigned access card. So the solenoid just pushed the card, as you can see. Now A1 is out, right? Now the carousel will return to the home index position. A1 is out from the system, right? Now following out with the this is now just checking in the database. Okay, so we have the student ID inserted in the name. We have the photo for the directory of the proof, and then sorry, I'll just skip back a bit. We have the access card link, which is the access card number. Now we have the slot number and the pulse now turned to empty, from empty to filled, right? And then the access card is now filled to empty.
Excuse me,
from the access card,
excuse me, you have 2 minutes left.
oh, okay.
Yes.
So yeah, the same system, vice versa, and yeah, overall you understand how the system works. It's pretty straightforward. I'll just run through the slides. All right. So the program, this is what the optical character recognition system looks like. So we have the program finding 1-1 and every number after that, because the common denominator for a student access ID is 1-1. So for this project, we use 1-1. And as you can see in the test direct process on image, you have the student ID displayed on the bottom right. Right. And then for the card exit, this is the internal storage. Because we haven't implemented the cloud system, we for now using internal storage. So we also did some test and trial runs on foreign language such as German. And as you can see, the optical character recognition did deliver and read some noise, but overall it has a 80% accuracy for the data extraction. Now for the tests, we did 5 tests with external light in a lit room and 5 tests with external light, and results came in with the external light is placed perpendicular to the card scanning station. And how did we determine the results to be valid is that if the A1 card shows A1 and the student ID shows the exact student ID. So the testing on student ID, we did 10 tests without external light and 10 tests with external light. Without external light, there's a percentage of failure of 20%, and with external light is 0%, so it's perfect. And on access card, we did 10 tests, just the same test. And without external light, we have 40% percentage of failure, and with external light, 0%. And these factors are due to dirt and deflection, and these are simulating real life problems of the cards in hand. So for the simulation test, we have 5 times sequence in and 5 times sequence out. And for each test, without the external light, we have a failure rate of 40%, and all failure are due to optical character recognition of access card, as you can see in the bottom right. And for the simulation test with external light, we ran 10 tests, and the failure rate is 0%, which gives us a reliable test. So as for future reference, this test definitely can be implemented into. It is a successful proof of concept and can be further developed for commercialization. It definitely require a better packaging, right? So that the user just don't take the cards from the outside. Right?
Thank you.
Okay, thank you so
Thank
much
you
for listening.
for interesting
Yep.
presentation, and
Yep.
the system is very useful. So, is there any questions for this presentation? Oh, sure, Dr. Teh.
Sorry, I can't hear you. Sir. I can hear you very slightly though. Yeah, I think your mic's not on.
The volume is very small.
Yeah.
Because maybe I can help you with the. Okay. How about the problem? The quality of the card is not really good.
Right. So, sir, do you wanna take over, Mr. Leo, or?
No, go ahead.
Okay. So we did some tests, as you can see. So the cards that are dirty and are very butak, if you can envision, very butak, yeah.
Yeah,
And
there's scratch like artifact. Like,
real, yeah. So to bypass this problem, implementing a high resolution camera would be the solution. And for sure, for OCR, for data logging, the less data we need or the less data extracted would be better. But for sure, in a card, there's so much information and so much dirt. Dirt can be considered noise from the optical character recognition. So I mean, the best we can do is implementing a high quality camera, a 4K camera resolution, and securing our OCR coding for sure.
Yeah, OCR also has threshold that we can tune. So I believe testing different smudges of the card and optimizing the threshold so we can accept some tolerance of noise. So what is acceptable and what is not needs to be optimized.
okay, thank you for Dr. Everett and Leonard. Is there any question? But first, Dr. Bagus, is it enough? Okay. Is there any questions? Okay, from Hidayat.
Okay.
Good afternoon, Dr. Everett. My name is Muhammad Hidayat. I want to ask you about during this pandemic, some shopping place require visitors to be having vaccinated and or have a negative COVID-19 status. Will this system be integrated in the future with information about the vaccination or the health status of the visitor themselves, so that there are no long some quickest and make it easier to if something unexpected happens? Thank you.
You have like 1 minute to answer the questions.
Yes, definitely there is something we can do to integrate. That is a great suggestion actually in the light of COVID-19. This system was originally developed before the pandemic. So now I think that is an even greater purpose and function. Thank you.
Thank you so much for
Thank you,
Dr.
Mr. Leonard and Dr. Everett.
Yes, thank you so much for the presentation and good discussion. Now we will proceed to the third presentation for the
Thank you all.
paper titled Traffic Flow Estimation Using Cloud-Based Traffic Velocities for In-Vehicles Application. Is the presenter present? Oh yeah, Dr. Lucas is here. Okay. Okay, Dr. Lucas, take your time.
Hello, Lucas Venner speaking. Can you hear me and are my slides visible?
Yes, it's clear and your slide is already seen.
Perfect. Then good afternoon. Unfortunately, we cannot meet in person today, but nevertheless, I'm very pleased to present some of my current research results within the Mechatronics session of the Morse conference today. And I'm a PhD student at the Institute for System Dynamics at the University of Stuttgart, Germany. And at our institute, we take a look at different applications of engineering with the systems and dynamical point of view. And I'm working in the field of advanced driving strategies, and today I would like to present some results of traffic flow estimation using cloud-based traffic velocities. First of all, why is it important and interesting? First of all, there's an increasing amount of traffic participants on highways that provide live traffic data of their own behavior. And there are some kind of navigation service providers, such as Google here or TomTom, which collect this crowd data and then aggregate into a better traffic velocity estimate. And this estimate is available via own APIs and can be requested by individual vehicle participants on a highway, for example. Another point is that the current traffic situation strongly influences the vehicle behavior, which means, for example, if one vehicle has a predictive cruise controller that adjusts the velocity choice according to curves or speed limit changes, then this predictive planning is always influenced by the current traffic situation. And if it's possible to estimate that traffic situation with a model-based representation of the state behavior of the traffic, which enables an adaptive and forward-looking planning of the own vehicle behavior, and this leads to an improved energy or driving management. Within the talk today, I would like to start with a short introduction of traffic flow modeling, describing the model equations and the discretization scheme. Afterwards, I would like to show the traffic flow estimation setup, where I'm going to show the measurement vector, which allows for the application to online available velocity measurements. Then I will show the extended current filter setup, which performs the estimation. Afterwards, I will go on with the application setup and show the available cloud data, and then show a simulation scenario, which I use to test the performance of the estimation setup. And finally, I will show some simulation results. So first of all, traffic flow modeling, there are typically two approaches. One is a microscopic approach, which simulates all individual vehicle behaviors. And this is typically quite handsome and difficult to parameterize because you need information about each individual vehicle on a highway, which is normally not available. Therefore, a macroscopic approach is used more often, which is based on partial differential equations. And they contain two traffic states, namely traffic density, which describes the amount of vehicles within a certain highway stretch, which means position, and then traffic velocity, as I already mentioned, in speed. And furthermore, there's a measure called traffic flow, which can be calculated out of the two aforementioned ones, and describes how many vehicles are passing one position within a certain amount of time. And beyond those model equations, and the first equation is the important one, the continuity equation, which states that the amount of vehicles within a segment changes with the amount of vehicle going into that segment minus the amount of vehicle going out of that segment. And then we receive this partial differential equation depending on position and time. And furthermore, change of velocity is described by an acceleration equation. And this consists of three terms. One is the convection term that simply describes the propagation of the velocity profile. Then there's an additional relaxation term that describes a damped adaptation of the velocity towards the current traffic density. And this is a very important relation in traffic flow modelings. And on the next slide, I will go into further detail onto this. And the third term is the anticipation term, which describes some kind of predictive adaptation towards density changes. So as I already mentioned, the function V of density describes a relationship that states how fast can vehicles go depending on the current traffic density. It is called the so-called fundamental diagram, which consists of three parameters and is shown on the right plot in the bottom, where you can see that one parameter is the free flow velocity that describes how fast can vehicles go if there's almost no other vehicle on the road, so the free flow case. Then there's a critical density when velocity starts to decrease due to increasing density. And furthermore, there's a shape parameter A, which describes how steep this change is going to take place. And as it is shown in this plot, this curve is being identified from real measurement data, which is also plotted in gray. And the takeaway message from this plot is that the higher the density on a highway is, the lower the velocity is going to be possible on this highway. Now I'd like to show the discretization scheme for the implementation. And therefore, the highway stretch is divided into n segments with a length of 100 meters in this case. So the continuity equation turns into an ordinary differential equation for each discretized position. And so we've got two equations for each segment, one for the density change and one for the velocity change. In order to put those equations into a state space formulation that can be used for an estimation setup, a state space representation is chosen of the discretized model, which contains all the density states for all positions from 0 to n, and all the velocity states in addition. So all the states are represented here. And then we've got the dynamics equation, which consists of all the individual and discretized functions which have been derived before. Furthermore, there's a noise added to the process, which is going to be considered in the extended current filter setup later on. Now, the important point concerning the measurement of online available cloud velocity information. So we have to define a measurement equation that describes the output of our system, and this one contains only the velocity information over the complete position, which means that we assume that we can request the velocity of a certain highway stretch from a cloud service and include it into our measurement setup. Additionally, there's an uncertainty or noise process with covariance matrix R. Then a typical extended Kalman filter is designed, where we've got in the first step the time update of the estimated state and the covariance according to the model equations F, and in the second step the measurement update is being performed of the estimated state as well as the covariance. And this can be done every time that a new measurement or new request from the cloud velocity data is available, and if no update measurement is available, the data is being used. Why is this relevant? Because later on I'm going to show that the online traffic velocity information is not requested frequently, but with an update rate of approximately 30 seconds. And furthermore, there are the Jacobian matrices as shown here. So let's take a look at the application setup. This is an example request from the cloud service provider here, where we are using the routing API, and this provides a traffic speed value for a requested route, and exemplary in this plot with a highway stretch of 30 kilometers. And we can see that the blue line shows the current traffic velocity, so the traffic speed on this highway. And additionally, there's information about the base speed, which describes some form of expected velocity on the highway, depending on historical data. So this does not include live traffic data. And as we see from this plot, especially at 15 kilometers and after 20 kilometers, we've got a lower traffic speed. So in this case, we would have some kind of traffic jam or condensed traffic situation. As we can see, those segments are piecewise constant, which means that we've got discretized position segments, which are variable in length. So this has to be considered when applying this online traffic speed into an estimation algorithm. Therefore, I analyzed the length of the segments and the occurrence. So mostly the segments are quite small and around 50 meters long, but sometimes they're even 500 meters long or up to 1 kilometer long. So this is going to be considered in the following estimation setup. Furthermore, the traffic velocity that is being provided by the online service is not always accurate, so there's an unknown offset to the real traffic speed. And the traffic data is also updated every 30 seconds, as I mentioned before. And for this study, I defined a simulation scenario where a traffic jam appears with a velocity drop from 80 kilometers per hour down to 20 kilometers per hour, as shown in the right plot on the bottom. And for this velocity profile, chosen as an initial condition, I defined random measurements as it could have been provided by an online service. With the gray lines, so we've got variable segment lengths and an unknown offset to the real traffic speed. And this scenario is simulated with the before and introduced traffic flow model. So we can see the initial condition with fast velocities and then slow velocities, which are going to change over time. So the traffic jam is going to move forward in position and is disappearing after approximately 300 seconds. Additionally, we can see the density, which behaves inverse. So first we've got a low density and then an increasing density due to the slow velocities, and then traffic jams disappearing and we're having normal densities again. If we apply the estimation setup to this scenario, then we can see the estimation error in those two plots for the velocity on the left side and for the density on the right side. And first of all, the 30 seconds intervals are visible. So every 30 seconds, there's a new measurement update. And then the traffic speed as well as the traffic density is estimated from the randomly generated measurement. So those two plots only show one specific case. And since we've got a randomly generated measurement, the study has been repeated for 100 times. So we've got 100 iterations with randomly created measurements. And in those two plots, we can see the root mean squared error once plotted over time, so the average over all states. And we can see that the average is quite small in density. Sometimes if there are small offsets in the measurements, there are also larger errors, but the mean over all 100 iterations still keeps very small and below 5 kilometers per hour. Same is observable if the root mean squared error is calculated for the spatially distributed states. So over precision, we can see that especially at the end of the highway stretch where we've got a lot of change, the error sometimes is bigger, but the mean is still quite low. And the overall estimation error is 2.31 kilometers per hour and 3.8 vehicles per kilometer in density, which is a quite small value if we consider the variable segment length and the offsets. This already leads to my last slide, where I would like to conclude that a partial differential equation traffic flow model simulation has been shown and an estimation setup was established that is able to reconstruct traffic states using only velocity information that is available online by navigation test riders. And this has been tested for an exemplary scenario with a typical traffic jam situation, which led to very small root mean squared errors for velocity and density. Next steps are going to include the application of this tested algorithm to real traffic scenarios, and therefore a measurement and a validation test drive is necessary, because if we want to validate the estimation of real traffic requests, then we also need some validation data of own vehicles driving on the highway at the same time. And furthermore, with the estimated states, model predictions shall be performed in order to predict the upcoming traffic situation over time. This is the end of my presentation, and I'm looking forward to remarks or questions, and thank you very much for your attention.
Thank you. Nice timing. Thank you, Dr. Lucas. Okay, now we continue for the Q&A. Is there any questions?
I have asked you one question.
Sure, Dr. Bagus.
I hope. Just a moment. There's a little bit problem with the feedback. So just now you said about updating the information about every 30 seconds, right?
Yes.
So updating information, according to me, depends a lot on the speed of the vehicle, right? So if you have slow speed, so you may reduce 30 seconds. But if the velocity is quite high, is that not too long to update the information? Could you explain about that?
Even if we take a look at 2 kilometers and then the update rate. So the problem is that the online services only update the information every 30 to 60 seconds. So there's no sense in reprocessing it more often, because then we only see the old data that has already been available before. And if we take a look at the scenario in this case of 2 kilometers, then we take approximately 90 to 100 seconds to pass through this segment. So we've got 3 requests within this time, and this is typically enough to see a change in traffic velocity early enough to react to it.
Okay, thank you.
We still have some time. Is there any questions for Dr. Lucas? Okay, thank you, Dr. Lucas, for your presentation. Now we proceed for the fourth presentation. The title is Prototype of a Multi-Story Motorcycle Parking Garage. Dr. Bagus.
Hello. Good afternoon, everyone.
Yes, Dr. Bagus. You may proceed to present.
Just a moment. Okay, hope we can see my presentation. Is it already shown in your screen? It's already
Yes.
represented. Okay.
Yes.
So I would like to talk about the prototype of multi-story motorcycle parking garage. So in Indonesia, the population is growing quite high, especially transportation is really important, and motorcycle is the most populated vehicle in our society. Motorcycles is an affordable vehicle for our people in Indonesia. So when you come to a certain place, you are a bit difficult to find available parking space. So required parking area need to be increased, because parking lot is right now is insufficient and difficult to find. And this also, if we cannot have a good enough parking space, so it will lead also to congestion in the street. Congestion parking is not good solution. It's an effective solution right now because construction and maintenance costs are not cheap. Also considerably less safe. Instead, risk of being hit by a car, loss, and also stolen. So we try to have looked to another solution, for example, multi-story parking system, and it is suitable solution for smart parking because it's responsive to user and it is a bit cheaper, actually safer than conventional system, and can be automatically operated, and some other features offered by the automatic parking system. For example, here we see in Japan they have a very high parking system, 3-level here, and for example, of course, you need a certain algorithm how to take out the car or retrieve a car from a certain place because it could be it is avoided to get out from the car. And we also have seen in Germany, I think, a lot of multi-story around like a cylinder form like this. So some places in Japan, I think they already developed a very huge parking place under the ground. And once again, you need a certain algorithm how to easily retrieve a car which parked really far from the entrance point. But all the examples are for a car parking. How about motorcycle? There are very few research demonstrating this kind of problem. For example, Setish designed a bicycle impeller, and Sunny designed motorcycle parking place for motorcycle, but it's limited only for frame analysis. For example, this is from Sati. It's they still have only for bicycle. Sorry, prototype. It's not implemented yet, but this is good for our case. They have designed a multi-story parking place for motorcycle, but they mainly consider only the analysis of the frame, not the total system we call an automatic parking or smart parking. And in this work, we try to design a parking place, automatic parking with 2-level, and for example, kind like this, so design in a real size, and we design 2-level parking system, which in each level we make an example of 3 slots. So we have totally 6 slots. And this work mainly focuses on designing the mechanical system and also designing the mechanism how to clamp the motorcycle to be inserted or to be parked and retrieved from the system, from the parking place safely. And then to also design a mechanism or algorithm how user can, for example, want to park the motorcycle and at a certain time they want to retrieve it at any time. So we make a prototype of this system and we produce analogy. So we design it almost exactly the same as our mechanical design. So this design can be resized according to user requirement. So for example, you want to make 10 level down there with let's say 10 so every level. It is still possible, very easy to extend it. The main concern should be the dimension of the stacker crane. So as the higher the stacker crane, you have to think about the stiffness, the strength, and also especially the column, because if you have very high column, there will be a problem with buckling. So we have to be really considerate about the stacker crane design. Okay, just as I said, just now design was live only for set load. All the members and prototype is made to visualize the principle of the system. The prototype was made using 3D printing. Experimental work to carry out to examine the algorithm developed to manage the storing and the retrieving of the object, in this case is the motorcycle, the miniature of motorcycle. Experimental work were also carried out to check the functionality of all actuators and sensors used in this prototype. And the algorithm developed in this system, we start with, let's say, showing a terminal for the user. There's a button, okay button, and retrieving button. So user come to the front of this panel. So the system will work continuously to check is there any motorcycle coming in front of this panel. So if there's one person coming here and they press the parking button, for example, the system will check whether this is task to retrieve or parking. Of course, in this case, to the right side of the flowchart here, it will park the motorcycle, and the system will check whether they come just 1 hour before the closing. If it's only, let's say, half an hour, so the closing very soon, so they would be accepted here. And then if it's still long way to the crossing point in the morning. So if it is full, there's no capacity. So it's also rejected. So the motorcycle also rejected. If the capacity is still there, so the parking action is taken. And then after the motorcycle is parked, of course, there need to be the number of the motorcycle side need to be created, as well as for retrieving action. If somebody retrieve one motorcycle, of course, there is no rejection. So just motorcycle from the place, and then the number of the motorcycles should be updated again. So let's make it simple. We have a main algorithm, parking and retrieving. Because here, when parking, after ready with all this procedure, and the front wheel will be clamped. After that, the body will be clamped, and then the sticker will come to the entrance, and then take the motorcycle inside to a certain place, which is assigned by the system. In this case, in this example, we assigned by ourselves, just for simulation. But for the rest of the system, there should be one algorithm, one module that has to determine which is the closest point from the entrance. So we try to optimize or to minimize the energy that we need to place the motorcycle in the system. As well as the retrieving, of course, the retrieving there's no problem because we know the position of the after, of course, the user showing the ticket from the panel, and since we will input the number of place where the motorcycle was parked, and then the sticker will go to that place, then the sticker will go inside and claim the front wheel and the back wheel. Of course, when I just forgot about saying the parking, and motorcycle has already parked, and now the parking place inside the system will claim the wheel and the front wheel as well. So the system puts the flow very simple, and then the uses Arduino Mega to monitor the input or input from, for example, the detecting of arrival, or the starting button, the keypad in this case to represent the scanning action, and then they already have their own motorcycle back and they want to get out, and we need output from Arduino to, for example, say what's going on, activating clamping for front and rear wheel, and activating sticker go to service. Okay, let's say we represent the algorithm using very simple electronics. If the capacity is there, so there is some empty space, so the system will say there will be position in the system, and you can start. If the capacity is not there or the parking is full, so you will see the display mentioning that the parking is full. If it's okay, so you see the motorcycle will come first in front, and then there is a kind of detect mechanism to take in the motorcycle. After that, of course, we need to clamp the body first. Because, let's say we have a motorcycle in vertical position, so you need to have at least one clamp in front and two clamp on the back side, so it will make the position of motorcycle steady during the parking process. And then after clamping all the important point, the sticker will take the motorcycle to sticker to inside the sticker, and it will bring it to a certain position that is designed. In this case, we design it manually, but for the future, we will generate algorithm to see where is the closest parking place from the entrance right now, because the closest position could be vary every time. Okay, it's not fixed. And you see here, the motorcycle, the already parked inside the slot. Of course, with clamping mechanism as well in this case. So that's the parking. How about retrieving? So in retrieving, you input the number where the motor is parked. In this case, actually, because we did it manually, so we know where it's parked. But in the real situation, we'll have a ticket. There is a barcode mentioning where is your motorcycle was parked actually. Okay, and then you just press start, and then here the sticker print will go to the target wherever the motorcycle is, and then of course the sticker will bring the fork going inside of the motorcycle, clamp all the important point, and then after making sure that all the mechanism works, and then the sticker will take out the motorcycle and bring it back to the reference point. Then it gives you that the user will should sit on the motorcycle, and then after that the clamping may release. Otherwise, the motorcycle will fall down. But it is still in the not implemented yet. Okay, so to improve the system, I saw a method in Japan that for bicycle parking, they have almost similar system. They clamp the front wheel, but of course not clamping the back side because it's very light. So they put a RFID tag. So we will use the same way, and we need to integrate the gadget of user. So automatically they can take out whenever they want. Integrated with a payment agent, for example, provide with optimization criteria for close scalable load, just like what I said just now. So let's say, because I have only 1 minute left, let's make a conclusion. This is a really simple system, but quite become a solution for our problem now. We can make a model, secret printing technology. The parking design was only for accepting motorcycle, and then it's only for 2 level 3 parking lots. And then it's already proof that motorcycle park and at the point where it's assigned. So I think that's all for my presentation. I hope this work will give you idea. And of course, there are still in accuracy, so we need to improve it in the future. Thank you very much.
Thank you, Dr. Bagus. Your interpretation would be very useful to save places in the crowd cities. Now, is there any questions for Bagus research? Okay. Okay. Thank
We
you
go
very
to the
much.
next.
Good afternoon, Dr. Bagus.
Oh, Fatan Hidayat.
Can you hear me, Doctor?
Yes, we can hear you.
I want to ask about this optical parking. In the process of waste,
Could you please repeat once again? Sorry, Fatan.
can you hear me, sir?
Yes.
In the process of inputting and removing the clamp, and also inserting or removing the motorcycle in the slot occurs automatically. So, what are the steps to be taken if the power supply used in the parking lot goes out, and are the clamps are safe in case of force opening or in the event of an earthquake or other shock, and whether these clamps can adapt to a variety of fields. Thank you, Mr. Bagus.
Oh, this is really difficult question from Fatan. Okay, the view, of course, this is real problem because we have underground parking. So we normally have emergency genset. Okay, so of course you need emergency genset, of course. Otherwise you cannot work for that. And earthquake, I just think about try to design the mechanical system as strong as possible. Okay, that's the only I can say. And also about the clamping, if you lost power, there's a special rules in designing clamping. So you have what we call it action clamp. Two action toggle clamp. So you need to really think about which is the action to clamp, because both direction has different forces. So you have to use smaller force for clamping and higher force for unclamping. So in case you have lost power, you can still release it. Otherwise, you cannot do anything. So there is a rule in clamping mechanism. I think that for now, that's all I can answer your question. Okay.
Thank you, Dr. Bagus.
Thank you, Dr. Bagus. Now we should proceed for the fifth presentation. The title is Sensor Placement for Qualitative Fault Diagnosability in Large-Scale Adaptive Structure. The presenter is already.
I hope you can hear me all right, and also see my slides.
Yes, it's okay.
Okay, very good. Then I think we can start. Hello, everyone, and now welcome to this talk on sensor placement for qualitative fault diagnosability in large-scale adaptive structures. My name is Jonas Stiefelmeier, and I'm a PhD student at the Institute of System Dynamics in Stuttgart. And now, before we dive into the details, I'd like to briefly motivate and introduce the concept of adaptive buildings. So the construction sector is responsible for around half the global resource consumption and additionally about 35% of the emitted greenhouse gases. So considering our urgent problems of climate change and the scarcity of resources, as well as the steadily growing human population, we somehow need to change the way in which we build in order to lower these numbers. Now I'd like to zoom in a little from the construction sector as a whole onto high-rise buildings specifically, because these require particularly much material in order to achieve the required stiffness so they can withstand loads, for example, due to wind. Now, if we just simply reduce the cross-sectional area of our building, then we get unacceptably large deformations and also make the building prone to vibrations. But instead of just using more material for passively increasing the building's stiffness, we could alternatively also just counteract those loads actively using, for example, hydraulic actuators, as indicated by these blue arrows. And then these forces provided by those actuators can be adapted dynamically, so also allowing them to dampen oscillations occurring in the building. And in that way, the resource consumption and thereby also the CO2 emissions. Now, to investigate the validity of this concept a little more closely, and not only in theory, a test building has recently been constructed at the campus of the University of Stuttgart, as you can see here in this image. So that's a 36-meter high test tower. And below the white facade, which is by now hiding the most important parts of the building, there's this steel structure with hydraulic actuators incorporated into some of the elements. Now, for actively compensating the effect of external forces, for example, we of course also need various sensors. Let me just display the pointer for estimating the system state, and then the controller can use this estimated state to determine the forces that the actuators have to provide. Now, given this large number of actuators and sensors and the long time over which such a building should be used, it's to be expected that at some point at least one of the sensors or actuators will fail, meaning that it stops working as intended. Such a failure would then directly influence the control loop and might therefore be quite uncomfortable for the inhabitants. And therefore, faults in the actuators and sensors must be diagnosed promptly and reliably so that appropriate countermeasures can be taken. That means that faults must first be detected, so meaning that we decide if there's a fault or if there's no fault. And in addition to that, they must be isolated or localized, determining which of the sensors or actuators is the faulty one. If and how reliably faults can be detected at all, of course, depends on the available sensors. That's what the term fault diagnosability means. Now, in this test building, we have a total of 48 strain gauges and 32 optically measured points. So we have quite redundant measurements, which is exactly what we need for fault diagnosis. In the future, however, those buildings should not contain unnecessarily many sensors. But of course, on the other hand, it must not become apparent during operation that we cannot detect faults in some of the sensors or actuators. So our objective in this paper was to ensure prior to operation of the building, and ideally even prior to its construction, that the planned sensor system allows for a sufficiently reliable fault diagnosis. And if that's not the case, then we want to extend the planned sensor system suitably. In the following, I'll now show the results of a qualitative analysis, which is a technique for determining which faults are diagnosable in principle. And then based on the results of that analysis, we can optimize the placement of sensors, meaning that we choose a subset of sensors from a larger set of possible sensors that we defined earlier. This qualitative diagnosability technique is based on the concept of the parity space, which has been studied quite a lot in the fault diagnosis community. In the approach, we start with a linear discrete time state space model, as shown here, and we accumulate the measurements over several time steps, resulting in this sort of sliding window model. And then by filtering the measured quantities y and u in a suitable way, we get to the so-called parity equations, which are shown down here. Specifically, that means by multiplying the measurements from the left with a basis of the null space of these matrices R and H, we can eliminate the influence of the unknown states and unknown disturbances, which leaves us only with the influence of the vector f. However, for these equations to be meaningful in any way, this null space must of course not be empty, and also the product of this null space with Q must not be empty, so it must not be the zero matrix. And then based on this, we can analyze the diagnosability of faults. We then call a fault detectable if the image space of its input vector is not contained in the image space of R and H, because only then does this left multiplication with the null space of R and H not result in an all zero vector. So only then can our fault still influence the filtered measurement here on the left-hand side. Similar criterion can then also be derived for the pairwise isolability of faults, where we just simply have to extend the right-hand side for the input vector of the second fault. To evaluate these criteria in MATLAB, I use these equivalent rank checks that you can see here, just since they are simpler to evaluate numerically. Here we have a small caveat, since we only evaluate pairs of faults for isolability. Multiple simultaneous faults can of course still have undistinguishable effects on the measurements. But in this study, we assumed that faults occur independently and only very rarely, and that after a fault occurs, it will be diagnosed very quickly. And then it's reasonable to assume that at any one time step, we only have to diagnose a single fault. Now, in order to evaluate the whole sensor placement, the detectability and isolability of all faults in sensors and actuators has to be evaluated with the criteria that I've just shown, leading to a detectability matrix D and detectability vector D and isolability matrix I. These then contain ones where the faults are diagnosable and zeros where they're not. So for the example of test building, I executed this leading to the isolability matrix here on the right, where the yellow elements are ones and the blue elements are zeros. And here you can see that most of the faults are distinguishable from all other faults. Only here, the actuator faults, we have a few faults which cannot be distinguished. Those correspond to actuators in the columns in the first few stories, as indicated by the pairwise identically colored columns here. So for those, faults are not distinguishable among each other. Okay, now since we want to evaluate different sensor placements and compare how well they perform in fault diagnosis, we use this diagnosability as a baseline or specification indicated by the index S. Okay, then finally we can formulate an optimization problem for the sensor placement, which is set up as follows. We're searching for a subset P of all possible sensors P full with the minimal number of sensors. And these inequalities down here then constrain the sensor placement such that the corresponding system does not violate our desired fault diagnosability. In two previously published papers, researchers Chris Sandra and Frisk have assumed a sufficiently long sliding window in the model that I've shown earlier. And in that case, adding a single sensor always renders a previously undetectable fault detectable. And in that way, they can then decompose this optimization problem into a set of easily solvable subproblems. However, for our test building here and also more generally for other large-scale adaptive buildings in the future, such an approach is not feasible since for our large models, these long sliding windows lead to numerical inaccuracies, both in this diagnosability analysis as well as later for the implementation of the actual fault diagnosis. So in this paper, I therefore consider a fixed smaller window length for which feasibility can be ensured. I then tested two different approaches to solving this optimization problem. The first one is called a destructive approach. In this one, I initialized the sensor placement as the set of all possible sensors, and then iteratively, I tried to remove each sensor in the set. If removing the sensor violated the specification, and if it was not violated, then the sensor is actually removed. And this resulting number of sensors in P is a local minimum of this optimization problem up here, as removing any other sensors would, of course, violate the specified diagnosability. In a second approach, I optimized sensor placements using a genetic algorithm. For this algorithm, I removed the inequality constraints up here, as it was difficult to enforce them throughout the mutation and recombination procedures in the genetic algorithm. And I instead introduced such a penalty term, alpha times V of P, where V of P here is the number of violations of these constraints. And if we then choose alpha sufficiently large, then we can ensure that the constraints are still satisfied at all the local minima of this cost function. Okay, so evaluating both of these approaches for the considered system, both approaches always led to sensor placements containing 14 sensors. So randomized execution led to different sensor placements, for example, iterating over the sensors in an orderly destructive approach, or randomly utilizing the genetic algorithm's population led to different sensor placements, but all of them contained 14 sensors. So the placement was not as important, but more the number of sensors, which I guess also makes sense intuitively. As you can see in the resulting isolability matrix on the right, the isolability was retained for all faults. We still have these non-distinguishable faults, which I've shown earlier, but of course, removing sensors cannot improve fault diagnosability. There were, however, no obvious patterns in how the sensors were placed, which is why I also analyzed a larger number of random placements in addition. So as all previous optimal solutions had 14 sensors, I thought it would make sense to evaluate 10,000 more placements, also with 14 sensors. And surprisingly, 69% of these random placements attained the maximal fault diagnosability. And all sensors occurred at a really similar rate in these optimal solutions with a standard deviation of only around 1%, meaning that no single sensor was chosen significantly more or less often.
Principal Mayor, you have 1 more minute.
Oh, okay. Yeah, then in order to check if specific cluster sensors preferably occur jointly or separately, I also analyzed the correlation between the sensors. However, there were also almost no statistically significant results with respect to that. I'll go over that a little more quickly now. So we could not ensure global, that our approaches find the global minimum of the optimization problem. I also checked another 10,000 placements containing 13 sensors to see if we can find better global optimum. However, none of these 10,000 placements attained the specified diagnosability. So if there exists a global optimum with this lower number of sensors, then it's much more rare than the local minima with 14 sensors. And that's most of the results already. So this diagnosability analysis that I've shown provides an a priori estimate for the performance of a fault diagnosis system, and could, of course, also be applied to other systems. Both investigated local optimal sensor placements with respect to this criteria. And for this system of an adaptive building, the diagnosability depended mostly on the number of sensors and not so much on their placement. However, this criterion that I use here lacks guarantees for the robustness of the diagnosis or the accuracy that we can achieve. Therefore, I, in the future, want to develop a quantitative analysis which also takes this reliability into account. And then in the following months, as soon as our adaptive test building will be taken into operation, I also will validate these results on real-world measurement data. That marks the end of the talk. Thank you very much for your attention. And yeah, if you have any questions, I'll gladly try to answer them.
Thank you, Dr. Sipel-Meyer. Is there any questions?
Yes, please. Yes, please.
Okay,
I've got one question. Mr. Sipel-Meyer.
Yes.
Okay, just now you said about the deflection of the building.
Yes.
If we look at from outside, we can easily see the deflection according to certain reference. How do you measure deflection when you put a sensor inside the frame itself or the structure itself? That's the first question. The second
Okay, so
one
we
is
have, oh, okay, sorry.
about actuator. Actuator, I think it should be two direction, right? It can be extended, also it can be retracted like that. Is that correct? For the actuators?
So these hydraulic actuators can only be extended, but since we have actuators in many of the different elements, we can still achieve any kind of deformation in the building. So we have redundant actuators, so only extending them still leads to a full manipulability of the building.
Yes, but
Okay.
if you want to try to minimize the deflection, of course you better give action here and the pull action and push action, right? To make
Yes.
it easier.
Yes,
Because
that
you
would be,
you put a lot of actuators, I saw, on every level, I think. Is that
yes,
right?
yeah, that's correct. Yeah, so we have actuators both in those vertical columns as well as in the diagonals, but yeah, they can only extend due to the, since they are hydraulic actuators. Of course, it would be ideal if they could also contract, but yeah.
How about the sensor? How about the sensor? Because
okay,
how do you
so
put that sensor? What kind of sensor do you use?
We have two main types of sensors. So one, we have strain gauges measuring the extension of our elements. So yeah, by how many percent they are extended. But in addition to that, we have cameras mounted on two sides of the building as indicated. So these provide absolute coordinate measurements. So that's quite important for observing the full system state.
Thank you.
Exactly.
Thank you.
Okay, thank you, Dr. Sipel-Meyer.
Okay, thanks for your attention.
Now we should see for the last presentation for the paper titled Evaluation of Novel Safety Concepts for Automotive Perception in Real-World Environments. I see Dr. Philip Stelzer is here. Dr. Stelzer?
Hello.
Hello.
Yes, I try to share my slides.
No, it's not shown yet. Please share your screen again. Now it's
now,
clear.
do you see my slides?
Yes, I can see your slide. Please proceed, Dr. Stelzer.
So, but my video isn't possible to enable it. Okay, should I proceed without video?
Yes.
Okay. So, okay. At first, warm welcome to my presentation about our publication evaluation of novel safety concepts for automotive perception in real-world environments. My name is Philip Stelzer. I'm a PhD candidate at the Institute of Technical Informatics from Graz University of Technology. At first, about the agenda, which is composed as followed. At first, I will give a short overview about the Pristine project where we are contributing in. Then I will talk about the sensor fusion platform, which we have used for our novel safety concepts.